Prova, prova. Sì, dai che entra, entra.
delle cuffie, non della...
Pausa, mezza, grazie a te.
Ma l'unico modo per sentire. Non so, adesso provo a vedere se su YouTube si sente, vediamo.
Ok. Allora, però la loro. Ciao.
Come vai? Bene?
Sei in
sento
ritardo
locale.
ovviamente, però
No, ma se ero qui prima, che...
Posso provare?
No, io in ritardo, non tu, ma va.
Vediamo un po'.
Ah, siete in ritardo qua?
Sì, per forza, perché sono sempre
Prova,
quelli che
prova.
ci sono e poi dopo il giorno ci sono. Già sta spina
Senti, noi riusciamo a parlare un attimo oggi
o a pranzo, viene a pranzo, c'è una pausa.
qualcuno di voi? Qualcuno di voi? Pausa, pranzo, va bene. Che allora ci lascia fare. Facciamo due chiacchiere show per riuscire a vedere se c'è la possibilità di fare. No, che ci può interessare, devi dire che con i tuoi ragazzi ci troviamo domani. Vediamo di capire cosa loro hanno bisogno.
Prova.
Sì, il computer là come lui mi ha detto, sai, il problema è che lui non sa di un altro, non è che c'è una lotta particolare, per cui proprio andare lì, se noi cominciamo a fare queste cose, adesso voi ci pagate, cioè, cominciamo.
Adesso si sente, dai.
Peraltro ci sono,
Ciao.
lo gestiamo noi questo.
Metti sulla tua, sì, gestite voi da
Bello, ragazzi.
chi è che vuoi? Daniele, tanto li metti sulla vostra.
Però io la vorrei vedere.
La posso vedere anche
Ti spiego perché.
So,
A meno che ce lo possiamo sistemare. Se lasciamo attiva questa.
so please, if you catch your seat, we can start again with the treasure that I invite in the front of the room. E se c'è Daniele in giro che può venire un attimo qua, non so dove sia, se c'è, per favore, grazie.
Qua chi è? Qual è? La nostra presentazione? No. Non è da... Mi sa che è da questa. No, sta uscendo dell'audio da lì. No.
Io che parlo?
No, ma dico, no, sta uscendo dell'audio qui.
Tu sei?
Sì.
Occhio che ti parli. Ti voleva Andrea, se non so.
Devo spiegare, è l'estensione di questo destro. Quello è l'estensione di questo destro. Ok? Però se tu vai avanti va a farmi là, dimmi se si vede.
No, raga, perché state andando qua? Perché siete andati qua? Perché al click si apre. Al click si apre.
Il laser è quello giallo. Anto, il laser è quello giallo.
Sì.
Il laser, Luca, il laser è quello giallo.
Se mandare la webcam o se mandare... Perché se le faccio così, cioè quello che dovresti fare tu, mandi la webcam. Chiaro?
Ok.
La prossima volta vi faccio un corso accelerato magari prima.
Sì, no, infatti.
Ma
Dove vi mettete voi?
noi siamo qui e in teoria abbiamo bisogno comunque di cambiare le...
Le slide le cambia.
Perfetto. No, aspetta. Non si... Una sola... Per cambiare le slide lo vorrei fare, cioè lo deve fare chi parla.
Basta che schiacci destra e sinistra. Parliamoci
non-
chiaro, se a lui non gliene frega, a lui barra lei non gliene frega di switchare dalla webcam al coso, io
iniziamo perché...
Io sono pronto. L'unica cosa è, se vi interessa fare il giro, cioè girare la webcam o il coso, allora Daniele sta qua e lo fa lui. Se invece non ve ne frega niente,
Esatto.
Secondo me
la puoi
lo
cambiare
facciamo alle
Però-
question and answer, basta. Quando facciamo la
Ok.
poi dopo lo facciamo. Lì avete il laser se vi serve.
Molla!
Cosa? No, bene così.
Raccomando, eh? Sì, allegro. Tommy, fai un duplica schermo. Duplica schermo.
No.
Ah, ok. Aspetta, Tommy. No, perché fai solo da fuoco.
Ok, prova se tu... prova a vedere se... Vai un attimo.
Sì.
Perfetto.
Tanti saluti, in bocca al lupo e a mai più rivederci. Questo comunque
È nostro per... sì, no, è utile. Ma invece di là...
tu sei di là, e quel computer è
Perfetto,
di
a posto, perfetto, grazie. Quello è lo schermo principale. Sì. Ok.
We want just to have, if the treasure can just squeeze over there, and we want to have here in front all the foreign students. Hello. Who are Ila?
Sushma, good luck.
E Andres.
Assumete come le tengo in mano.
Tu.
So you have to learn Italian to read it, but this is it for you, and thank you for coming to Milano to study.
So thank you, Professor Bernelli, for that. And now we can start with the treasure and keep on going.
Parla di qua.
So we can start. Good morning to everyone. I'm Antonio La Monarca and I am in charge of thermal control system. I am the team leader of the treasure team. It is a pleasure for me now to present our mission to Titan. We are Treasure, that stands for Titan Research Autonomous and Submersible Remote Sensing. And so we have to go to Titan, that is our main mission objectives. We have to make a global map of Titan with an higher accuracy with respect to the Cassini-Huygens mission. And of course, we have to analyze the composition of surface and subsurface. Before the Titan approach, we have to spend some time in the Phoebus ring, where we can collect its particles. As requirements for our mission, we have a launch date later than 2020, and we have to perform the global mapping with bistatic SAR that could be implemented with a formation of 2 satellites. Titan, you know, is a really interesting science target for us because it has a rich, dense atmosphere of nitrogen, and of course, due to its hydrocarbon lakes presence. But of course, it has also meteorological cycle of methane, like the water stay for the Earth. As our main drivers for our mission are the environmental one. Phoebus ring is one of the most challenging one because due to its particle density, it is very low. And you know that particles inside the Phoebus ring can vary from 4 up to 40 micrometers in diameter. And of course, our selected strategy is to make multiple flybys inside the Phoebus ring. About the peculiar Titan environment, it was interesting to highlight the lakes, the polar lakes properties. We can find methane rich and ethane rich that will cause ice to float or sink. As our landing site, we choose the Krakenmeer, that is a North Pole lake, where that has an extension of more than 1 kilometer. As our mission architecture, we choose to, we have launch in 20 and 26, and on Delta IV launcher, and power rated by the SEP module, we perform 80 years of interplanetary travel, and until we reach the Saturnian system. There, we stay for about 3 years, and collect dust for more than 1 year. After that, we reach Titan, where we have 600 days of Titan mapping, where we can can be accomplished by a bistatic formation of a master and a slave. Finally, we land on Titan, where we can perform surface and subsurface science for more than 3 years. Now I leave the floor for Luca, that will explain you our mission, starting from the mission configuration.
Okay, hi everybody. I'm Luca Di Pancrazio. I work for the structure subsystem, and I'm going to present you the Treasure spacecraft. From the Stevenson novel Treasure Island, our models, our spacecraft, is composed by 4 models. Each model is named like one of the characters from that novel, and we can see from top to bottom, we can see the lander module composed by the Hispaniola and the diver Jim, the slave module composed called Flint, and at the bottom the master module called Warless, and in the end the SCP module that give us the electric propulsion for the interplanetary transfer. Now, this is the alignment for every of the models that I explained. So the slave, Flint, the master Warless, and the SCP. Now, this is the configuration at launch. All the vehicles are attached and one on top of the other, and give us these vehicles. The vehicles has a total height of 9 meters and a total weight of 4 meters. And all the scientific instruments are attached on the external surface of our spacecraft in order to look outside at the space environment. When we reach space after the launch, our solar arrays deploy, as you can see from the model on the desk, and from the slides. We reach a total height of 25 meters for a total height of 12 meters. This is our spacecraft during the interplanetary transfer. Then, after 3.5 AU from the sun, we just detach the SCP module and we start the transfer just with chemical propulsion that you can see under the master module with the 3 main engines. At the arrival on Titan, we just the module just detach in the Flint and the Walrus, and in this way we can perform a bistatic mapping of Titan, and at the end of the mapping we land on this surface. Okay, the landing is a soft landing, even if we encounter a solid surface or a liquid surface, because we want to land on the lakes, but we can meet ice probably. So we design a proper lander that we call now that I recall that is called Hispaniola, and Hispaniola is pretty cool. Hispaniola can move on the liquid surface with propeller, and it can correct its position if it lands in a wrong way. What I mean is a wrong way. If it lands with its belly up, for example, it can roll in the water in order to point the antenna towards the satellite. Now, and now with the presentation, we will explain all the phases for our mission, and for each phase we will explain which is the critical subsystem that is working in that particular phase. So we start from the launch, obviously. And for the launch, the most critical subsystem involved is the structure. Now, for the launcher vehicle, we must select the most feasible vehicle for the launch. Given our mass at this stage, that is 7.1 ton, we had just two vehicles, just two launchers available. That are the Falcon Heavy and the Delta IV Heavy. Since the Delta IV Heavy is more known, even for the acceleration, the modal coupling, all this stuff, we selected the Delta IV Heavy for the launch. So, returning to the structure. The structure is a semi-monocoque structure made up from panels, strings, ribs, obviously, that are made of titanium and aluminum alloy, for a total weight of 580 kilos. Just in order to fulfill the requirements, we made some analysis, some model analysis, and we presented you the results, like the margin of safety for the axial mode and flexural mode. And we can see that from there, and even from the static. Even from the static loads, that we are good to go. We have good margin, and we are launchable. Just a little focus on the displacement. You can see that during all the voyage we have the maximum deformation, that is the maximum displacement that is inside the fairing. So in this way we can see that even at the maximum axial acceleration we are good to go. So I finish for the structural environment. I leave the floor to Andrea.
Thank you, Luca. I'm Andrea Marcovati. I am in charge of the solid electric propulsion subsystem. And now I will talk to you about the interplanetary travel, in particular the emission analysis and the two most important subsystems that are the solid electric propulsion and the attitude dynamics and control system. Most important for this phase, of course. About emission analysis, of course, we want to minimize the amount of propellant consumed. And in order to do that, we minimize the interplanetary delta V, keeping low the exit velocity from Earth's sphere of influence, which is a constraint on the launcher, of course, and the incoming velocity in the Saturnian sphere of influence, which is a constraint, of course, on the capture. So the solution was to implement a low thrust optimization software that simulates the low thrust trajectory as a series of distributed impulses. And the result was quite pleasing, a mass ratio of 0.925. That means that just 7.5% of the initial mass is xenon, expellant for the solid electric propulsion. Here you see the trajectory. The green lines, the green arrows are the distributed impulses. It's worth noting that we cannot exploit, we do not exploit Jupiter because it's unavailable for our time window. We make 3 gravity assists. So these are the solutions in terms of dates and the time of flight. Here you see a quite low departure velocity, a quite high arriving velocity to Saturn. This is due to the fact that we cannot exploit Jupiter to speed up to Saturn's speed. Okay, these two plots. The first one is the thrust profile as a function of time. The peaks are when we are near the sun. Of course, we have more power available. And the mass ratio profile as a function of time. Okay, about the electric propulsion, we decided to use solar technology since we didn't want to bring with us a nuclear reactor. The choice was driven by the fact that we want a thruster that is proven, ready to fly, able to work continuously and be switched on and off. We also want light and as small as possible solar panels, and they can be stored in a low volume. So the solution was to use NASA's next thruster, ion technology, and high efficiency triple junction solar cells and flexible solar arrays. Okay, we have to provide a thrust that is one desired by the mission analysis. In order to do that, we can play with 3 parameters. The input power, the mass flow rate, and the number of working thrusters. What we want to do is to maximize the specific impulse. As you can see, we always try to follow the maximum power available because each single thruster has its high efficiency point when it works with around 7 kilowatt. And around 7 kilowatts. So if for some reason there is a lower power available, it has to increase the mass flow rate in order to provide the same thrust. As you can see here, we are near the sun. We have much power. Much power available, but we cannot use it all because we just have 4 thrusters. We would need a 5th. And here we use all 4 thrusters, and we can use them at high efficiency. You see the specific inputs around 4,000. Here we are far away from the sun. We have low power, so we use only 1 thruster, and we're still able to have a specific impulse of around 4,000 seconds. Another criticality was on the perturbations, because we have big solar panels, 82 square meters, and these huge solar panels provide for a big torque on our system due to solar pressure. If we were to compensate this torque only with hydrazine monopropellant, we would spend 370 kilograms of hydrazine. So what we did was a twofold strategy. First, when the thrusters are working, we use the gimbal mechanism on the ion thruster to also to control the attitude. And when the thrusters are not working, we put our spacecraft in such a position that the solar pressure doesn't generate a huge torque, which is basically here and here. With this strategy, we're able to decrease the mass consumption from 370 kilograms to just 10. Okay, that's it. I leave the floor to Matteo Losacco, who's going to talk about the Saturn tour. Thank you.
Okay, good morning. I'm Matteo Losacco. I'm in charge of mission analysis together with Maurizio. Today, I show you the main topics of the Saturn tour, and so I'll start with the mission analysis. The mission analysis in this phase can be divided in 2 parts. A first part where we have a progressive reduction of the energy of the orbit, whereas a second part where we get to Titan. We have seen from the interplanetary transfer that the entry velocity in the Saturn sphere of influence is around 5.8 kilometers per second, so it's quite high. We have a lot of criticalities for this phase. We know that we have to maintain quite low the initial closure cost around Saturn. Moreover, we know we have to stay enough time inside Phoebus dust. So we have a lot of criticalities, but a lot of degrees of freedom. For example, the selection of the actors for the tour. We know, for example, that Titan has a high perturbation potential when the energy of the spacecraft is high, whereas Rhea, for example, has a lower perturbation potential when the energy of the spacecraft is lower. So we decided to exploit this kind of strategy. So we did first deep space maneuver at the entry of the sphere of influence, then a power gravity assist on Titan, and then a leg from Titan to Rhea. This leg has been designed in order to obtain, after Rhea free gravity assist, a resonant orbit on Rhea itself. At this point, we have the initial condition for the resonant tool. So we have a progressive reduction of the resonant ratio up to 5. When we reach 5, with free gravity assist, there's no way of decreasing the resonant ratio because we reach a level of saturation. But in this case, with power gravity assist, we could decrease this value up to 4 and 3. When the resonant ratio is equal to 3 and we are at this point, there's no way of decreasing the resonant ratio, whatever delta V is given. So this first phase ends. But with this first phase, you can see in yellow, we can spend enough time inside phase dust, and more, we could limit the closure cost around Saturn at less than 1 kilometer per second. But at this point, we have the initial condition for the second phase, which is approach to Titan. We decided to design this approach with exploiting three body dynamics, and this is the strategy we developed. You can see in black here, this is a last resonant orbit expressed in the rotating reference frame of the Saturn-Titan system. And as you can see, the intersection of this orbit with external stable manifolds are not so good at the very beginning. But if you stay on the same orbit for a holding phase, the intersection changes. So what we decided to do is to set a first holding phase on the resonant orbit, and then a transition from the resonant orbit to the external stable manifold in this point, and after 2 orbits and a half. The external stable manifold inserts the spacecraft into an halo orbit around L2, and here a small perturbation is given in order to insert the spacecraft into an unstable manifold, which is exploited to reach a closed orbit around Titan. Actually, this closed orbit is not the final target one, so a reshaped maneuver is needed. So the results are the following, with an overall delta V, which is a little bit more than 2 kilometers per second. You can see the list of maneuvers. This is just one maneuver, whereas this one is a summation of the final cost, the cost from the manifold to the parking orbit, and from the parking orbit to the final target orbit. This strategy was quite good because with the combination of the resonant tool and the manifold, we could save around 300 meters per second. So this is why we selected this. More, we can see the time spent inside the dust according to the model of the dust we had, according to the different size particles. And we can see that we spent more than 1 year inside the dust. So this was the reason why we selected this long travel. At this point, we can see which are the most important subsystems for this phase. Differently from the interplanetary phase, here we have chemical propulsion. And the selection of the engine has been done according to the most critical system, most critical maneuvers of this phase. You have seen it before. So this is the architecture, and these are the results. Another system which is critical for all the phases, and we decided to present in this part, is the thermal control subsystem. The first step in the sizing of the thermal control subsystem is the identification of hot case and cold case. Hot case has been identified in Venus flyby in interplanetary transfer, with front shield pointing toward the planets and radiators pointing toward deep space, whereas the cold case has been identified in the entry of the sphere of influence. Now, starting from this, the general architecture involves the use of MLI on modules and tanks, and use of louvers on radiators, whereas the active control techniques are different for the different modules. In the master, we have heat sources which are external, but they can be exploited during cold cases, whereas in the slave, we had RTGs which are in the front shield, and we need to dissipate heat. So we developed a heat rejection system which uses as working fluid ethane and not freon, because ethane was compatible with Titan's temperatures. And so the working fluid takes the heat from RTGs and take it to cruise radiators. So starting from this architecture, according to a multinodal analysis, we have results for the master, and you can see the most critical case for the master and for the slave. And here again, the most critical case is linked to a propellant. So now I leave the floor to Tommaso, who will show you the mapping phase.
Just a few seconds, they are going to prepare the presentation. So we can start with the mapping part. So we want to globally map Titan by means of bistatic SAR interferometry technology implemented on a formation of 2 satellites. The big challenge is to have an accurate and unambiguous model of the surface of Titan, and in order to do it, the formation has to guarantee at least once big baselines at all latitudes. In order to satisfy this requirement, we're going to exploit as much as possible the effect of natural perturbation on the relative motion on the formation, and in particular the natural perturbation relevant are the third body effect of Saturn, the drag, and the J2 effect. Starting from the observation orbit that will be occupied by the master spacecraft, the master spacecraft will orbit at 1,720 kilometers with an inclination of almost 73 degrees. From this orbit, a full coverage of the equatorial circumference will be guaranteed in almost 100 days. The SAR performance guaranteed on this orbit are characterized by a range resolution up to a maximum, up to a minimum, best range resolution of 1 meter, best azimuth resolution possible of 1.5 meters. The ambiguous 8, important for the digital elevation model, will be at minimum 8 meters. The formation will be characterized by a nominal separation in radial direction of 250 meters and in cross-track direction of 3,400 meters. As I said, it's important to look for, to guarantee big baseline at least once at all the latitudes. So what we did, we studied the free perturbed motion deformation, and we found out initial condition in terms of relative orbital parameters of the mass of the slaves that guarantees a perturbed motion that causes a shift of the point at which the baseline is maximum progressively from the polar regions toward the equatorial regions in 600 days of mapping. On this concept is based our mapping strategy. So in the first 200 days, the maximum baseline will be comprises in between 60 degrees of latitude and 90 degrees of latitude. It means high resolution mapping of the polar regions, whereas the equatorial region will be characterized by badly mapping, and moreover, there will be zones that are shown here in the plots, in which the interferometric SAR is not applicable since the cross-track baseline is lower than 500 meters. The first phase is characterized by 2 modes. The modes A, in which are going to map the North Pole, the modes B, in which are going to map the South Pole. To pass from one mode to another, we're going to exploit a simple slew maneuver from plus minus the look angle of the instrument. So after these first 200 days, we pass to the second phase. We are exploiting the free perturbed motion. So in between 200 and 600 days, the maximum cross-track baseline will be comprised in between 60 and 25 degrees of latitudes. Therefore, we have a high accuracy mapping of the equatorial region, whereas the polar region will be mapped with low accuracy. All the mapping is redundant since all the modes are repeated twice in each of the phases. As I said, this strategy is cost-free, we can say, because we are exploiting the perturbation, but in reality, it's not, since we have to correct both in a long track and cross-track our formation. In particular, the slave spacecraft will perform one maneuver every 20 days for formation keeping, and moreover, station keeping maneuver every 100 days together with the master. In order to accomplish the requirements in terms of modulus of delta V and delta V orientation, we set up a configuration of the thruster characterized by 12 plus 12 thruster for redundancy. The thruster will be oriented on the body, along the body axis, and they guarantee a full control, both translational and rotational. That is really good also for attitude control. Talking about the attitude control of our master and slave spacecraft, we have the strong necessity to orient the antenna toward the ground strip that has to be illuminated for both the master and the slave. Therefore, we have a fixed axis, this is the Hayangena pointing axis, but we have a degree of freedom. The degree of freedom is characterized by the orientation around this axis. So we look for an orientation around this axis that can minimize the effect of gravity gradient perturbation. And we found out the right orientation, and therefore we can spend a really few propellant in order to control the attitude of our spacecraft thanks to this stratagem. So obviously we are talking about SAR instrument, therefore we have to download the data of the SAR instrument toward Earth, and before we have to store the data. In order to download the data of the SAR towards Earth, we designed two download links, one from the master and one from the slaves. The necessity to download the data is really frequent, therefore we are going to download the data once every 6 orbits. It means that the 17% of the 600 days of mapping will be occupied by telecommunication issues, by telecommunication download. The two links are characterized for the master and for the slave by a precise amount of data for each window, a precise required data rate, and pointing accuracies. Passing to the onboard data ending, we need to store a huge amount of data, for up to 4 terabits, and moreover, the attitude control has to guarantee needs high computational power. The architecture that we study for the onboard data ending is characterized by a central space router with 2 interfaces, one for the master, one for the slave, and one connection of the slave, one connection with the SEP. The payload is characterized by the closed-ring configuration with a peculiar router for the management of the system. The configuration for the slave and the lander is really similar. The only difference is that we have 2 more interfaces in order to detach the attitude control system and the payload of the slave when the lander has to land. So we can leave the floor to Roberto for the Titan exploration part.
Okay, I can start. Okay, just one moment. Okay. I'm Roberto Travaglini. I'm in charge of the attitude determination and control subsystem, and I'm going to talk about the last phase of our mission, the Titan exploration. So while the master remains in the scientific orbit, we are going to perform in situ science with our lander modules. Of course, the first part is the landing. We are going to land in the Kraken Mare, but the exact spot will be chosen accordingly to the data obtained during the mapping phase. So the slave is going to fire its main thruster to put itself in the entry orbit. Then it will detach from the lander before entering the atmosphere. The atmospheric phase is characterized by 3 different parachutes, with the last one being the stabilizer that will be detached 10 meters above the ground to avoid entanglement with the lander. Of course, we have to check the uncertainty of the landing site, and to do so, we use the Monte Carlo method. And we add as variables the flight path angle, the out-of-plane angles, the drag coefficient, and the atmospheric composition. But as we can see, all the distribution is quite close with the nominal plane of our orbit. And in the right plots, we can see that all the distribution is confined within 50 kilometers from the nominal site, and this data will be very important when we are going to choose the landing site. During this phase, the entry, the most stressed subsystem is the thermal one. So from the data, from the trajectory from the mission analysis, we estimated the thermal loads, and therefore we designed the minimum required thickness of the heat shield and of the back shield. Then another criticality of the thermal control subsystem is the fact that from the cruise radiator separation to the front shield release, all the waste heat produced by the MMRTGs are going to be absorbed by the lander. So we had to study this transient phase, but as we can see from this plot, at the end of the transit, we are still within the survivability temperature range. Another critical point is the onboard data handling, because we need a high autonomy and a high computing power to perform all the in-situ science, surface and subsurface that we need. But the most critical point is the connection between the diver and the floater. Our architecture has a fiber optic cable that will, but this will be needed to be heated up because of the very low temperature of the Titan lakes. The other solution is that we have a magnetic interface that will work when the diver and the floater are attached together. This architecture is intrinsically redundant because if the tether management system, that is the one that rewinds the tether, fails, we are going to keep performing our science and communicate with the fiber optic. Whereas if the fiber optic fails, we're going to rewind the diver, reattach the diver and the floater, and communicate through the magnetic interface. Then, of course, we have to send all the data to the master. And to do so, we send it from the floater using a UHF antenna at all the available time windows. The last critical subsystem is the electrical power. Why? Because we have 3 different modules, the slave, the diver, and the floater, that has to be powered together by the same system. And also, another criticality is the performance losses due to the MMM RTGs being inside the heat shield. So our architecture has 2 full capability PCDU that works, one for the floater and one for the diver. And during the mapping phase, they work together to power the slave. Then, about the MMM RTGs, the easier solution is to migrate to enhanced MM RTG that should be ready by early 2020. If they won't be available, we can design the extraction of the MM RTGs while we are on space. Finally, towards about the end of life, we are going to crash our master in the equatorial region in order to avoid more important scientific regions like the polar lakes. And now, I leave the word to Riccardo.
Good morning to everybody. I'm Riccardo Micheli, and I'm in charge of the chemical propulsive system. For now, I want to focus your attention on budgets, cost, and risk analysis. Let's start with the mass budget. As you can see, preliminary analysis bottom-up for the entire spacecraft, resulting in about 3.2 tons in dry mass and wet mass of about 7.1 tons is shown. And for what here you can see a mass breakdown for the Walrus module with an overall wet mass of about 4.5 tons. And for what concerns the Flint module is actually considered as a system with the lander module for what concerns the overall pie chart, and just the Flint module and his subdivision just in that area. This is due to the fact that the Flint module will operate exploiting the electrical power system and the onboard data handling of the lander in order to save mass for the mission. What is characterized by the mass breakdown of Hispaniola is the high percentage dedicated to the structure and to the thermal control subsystem. This is due to the fact that the system has to withstand the touchdown loads and the severe environmental condition of Titan. While GIM is the module with the highest percentage dedicated to the payload and to the electrical power system. And this is due to the fact that it is the one to make science on the lake bed. For what concerns power budget, once again, we consider a bottom-up approach, subdivided in modules. And in the graph here, you can see the power demand for each module operated by the Walrus module. And here are just highlighted the columns relative to the most demanding phases, modes, with the power breakdown into subsystem. Same has been done for Flint, that once again has been considered as a system along with the lander module, and the demanded power has been fulfilled thanks to the overall lander electrical power system constituted by two MMRTGs plus 3 batteries for the peak values. On the graph, like the previous one, we can see the power budget for both Hispaniola and JIM, which are performed thanks to the MMRTG mounted one per each module, plus 2 secondary battery on Hispaniola and plus 1 battery on the JIM module. Talking about the risk analysis, we performed it taking into account the risk matrix method. And here I just presented the 2 high risk that we identified, which are the fiber optical cable damage and the MMRTG not working in operational range. Of course, those values are not acceptable. Therefore, we try to think about possible action to mitigate this factor. Therefore, what we thought was to establish a series of experiments in order to reduce the likelihood of this failure, while for the MMRTG case, we are thinking of migrate to eMMRTG that, thanks to the higher efficiency and the higher operative range of temperature, would grant us the reduction of the severity, hence allowing us to reduce the risk index for both the situation. About cost analysis, we have considered several models, but then discharged because we're relative to small spacecraft. So finally, we ended up analyzing through an analogy-based model. For this purpose, we considered Cassini-Huygens mission and applied both past and predicted inflation in order to obtain an overall value of about $4.2 billion. Further development would require a bottom-up estimation. Here is just a development cost breakdown in terms of statistical for the subsystem, even though it might not fit perfectly with our mission due to the innovative nature of the mission. At the very summary, I would like to summarize what we have seen so far. So we're talking about a flagship mission. So likely, we would like to have, it's likely to have an International Space Agency collaboration. And among the few open points highlighted, the next work could focus on the reliability on the cable system and on the lander mobility, while the possible improvement to the design to increase the reliability of the system could be the establishment of the VHF communication link between Hispaniola and JIM in case of failure of the cable. Finally, our presentation, our development of the mission would require several tests. We had the chance to run a lab-scale lander test, work on some splashdown and self-rightening rollover test. The splashdown test was considered in 3 different modes, the nominal one, the lateral, and the upside-down one. And the result led us to a good buoyancy and stability, a successful self-rightening rollover, with the phase duration of the splashdown phase of about 1.2 seconds and a self-rightening rollover phase of about 1 second. And here, we would just present our a brief video of our test run here in the laboratory as soon as it's uploaded. So right now, we would just present how we scaled the module and we built through stereoform and weight placed in a proper position in order to place the center of gravity in the proper place. Here we have a fast camera which has 200 frames per second, which allowed us to have these high resolution images. And this was the very first one. This is the second configuration, so lateral. And finally, we can see the upside down configuration. And at the very end, this is the self-right rolling of test.
So at very end, the last thing I just want to show you, I just want to show you the final video of a few seconds about our overall mission, and yeah, this is the interplanetary travel with the SEP module. And so we are, there is the approach on Titan, then we can map with the slave module, and the master one, it is the detachment. And this is the lander of the land of the our probes on the Titan lakes. With parachute, the front shield opens, and then the diver and floater can develop their science, subsurface and surface science. I hope that you enjoy our presentation. This is our team, as we are divided into subsystems. So I thank you for your attention, and please feel free to ask us any doubts or questions. It was an interesting comment. About risk analysis, we just want to present some of the main risks that can affect our mission. Of course, it is a complex mission, and of course, we have a lot of risks that can be analyzed. And for the last point, we about methane on literature, we don't find a lot of stuff, but we are with the information that we have, we just try to cite the floater and the lander diver, and so we try to choose the material, but of course they are tests that has to be at first take on art in order to prepare. Yeah. It's fragile. Yeah.
So it's necessary to use some element to increase the robustness.
Okay.
I think it's interesting, but it's not a detail.
Okay.
It's a point that demonstrating feasibility of this kind of.
Thank you. Thank you.
Well, this is a competition, as was just pointed out, and I was wondering how you plan to deal with operations around Titan. I mean, you have different modules, and then you have a master-slave configuration, you have to perform maneuvers. Is everything completely autonomous? Do you have linked ground?
I think, sorry. I think that ground in the loop control is, because, for example, for the formation control, we identified some preliminary scheduling of the maneuvers in order to control all the strategy of the mapping. But in any case, it's important to have a feedback once arrived on Titan on the real situations. So it's important that, taking into account the telemetry, the Earth received the data, and in a scheme that is a ground in the loop control also scheme, can control the formation. But the important thing is that the maneuver of formation are not so frequent to request a really, you can say, really frequent ground in loop control. So you can start with a predefined sequence, then check the situation, and with a feedback from Titan, and the ground station can update the sequence of control and therefore perform the formation. But the ground in the loop is necessary, surely, because it's not fully autonomous.
Okay, so starting from the data point of view, our data storage, our solid state recorders are really, really big, and they are designed to record data for 100 days of mapping for the master and for the slave. So since we transmit the data to the Earth every 16 orbits, we are really pretty much space to store all the data and telemetry and all the other things in case we lost, for any case, the communication with the Earth. Of course, the computers that we have on board on the master and on the lander slave is really powerful. So we can manage to analyze some kind of data inside by the master, and so decide how to perform the rest of the mapping, or to do something different in in situ science. And the computer are designed to withstand also the autonomy, complexity, and so all the other operation that in the future, in the 2026, the spacer could be able to do, and now it's not possible, of course. I hope I just.
Let's say, a standard planning cycle, even if it's a very long planning cycles for the intervention of scientists in these missions, or just you intervene based on figures?
we have, of course, we pass to safe mode in case of any failure, and we hope that the computer for the power computing could react to the failure, so for some failure, of course, but we are not designing the software, and some part of the software is just conceptual blocks, so it's an open point, and we will try to develop it in the future.
So I just spent the words to defend them on questions that we did, in the sense that, of course, the risk analysis may be poor, but the focus was on, I know that the technical part should be, let's say, accompanied by the risk analysis, I mean, step by step, but the months
Scusi. Yes. Good morning, everybody. I'm Matteo Beguera, last team leader of Ardent team, and specifically in charge of OBDH subsystem. Ardent is the name of our mission. In fact, Ardent stands for Hidden Refueling Depot Network. And our mission is about creating an infrastructure capable of supporting a recursive manned mission on Mars. The round trip from Earth to Mars is supposed to be of 250 days of duration, and the payload of our mission is a Columbus-like module of the mass of 10 tons. The design drivers we selected to design our mission are the following. Of course, the robustness to failure, crew safety. I would like to remember you that our is a manned mission. Second driver is the minimization of propellant mass to perform our servicing. And of course, we decided to strictly respect the mission assignment. Of course, in order to achieve all of this, we have to accept the consequent increase of complexity, both in terms of low-tier hull in many mission segments, and also, as you will see later, we have an extremely articulated mission design. So, launch windows for Mars opens each 2 years, but considering an epoch that starts in 2013 and ends in 2056, some launch windows are much worse than others. We go from a best case of 28 kilometers per second to a worst case of 47 kilometers per second to perform the round trip. And one of the main challenges of our work was about creating an infrastructure capable of adapting on such a gap in the cost of the mission. So, as a first evidence, let's use a Tsiolkovsky law with our payload mass, a standard structural coefficient, and the delta V of our worst launch windows. We see that we are obliged to use both on-orbit staging. It means we have to use 4 stages to have a reasonable mass, and we have to perform at least 2 refueling, one in Earth system and the second one in Mars system. So it brings us to use large structures to perform our mission. This is a fast comparison with the International Space Station. So we could select various locations for our propellant depot in order to perform the refueling. First option, we could assemble our spacecraft in a LEO orbit, perform the refueling on Mars. It means that we assemble our spacecraft in a low Earth orbit. The manned mission starts. We perform the refueling in Mars system, and then we come back. Another option could be perform the refueling and assembly of the manned spacecraft in a low Earth orbit, then refuel before braking at Mars, refuel before leaving from Mars, and refuel before braking at Earth. Another selection could be Earth-Moon-Lagrangian point 1, and of course, as I said before, we need refueling in a low Martian orbit. This is the strategy we selected. So let's compare some propulsive system. We see immediately that the only reasonable masses we have to perform our servicing, also in terms of launches needed to perform our servicing, is to use nuclear propulsion, which is a low and high risk choice, but is pretty much obliged for us. So, which are the risk drivers for our mission? Of course, the crew safety. How we can mitigate it? By using simple as possible operation on the manned mission. How can be simple operation on the manned mission? Moving complexity in refueling mission, so in propellant location. Let's see the last trade-off about propellant location compared using the same propulsive system, which is the nuclear one. We see that we achieve a reasonable number of launches using Earth-Moon-Lagrangian point 1 location. And we see that the strategy with the 2 deep space rendezvous illustrated before is not recommended because to the high risk and complexity of such a selection. Between the advantages of Earth-Moon-Lagrangian point 1 as a location for a depot, we have the more complete utilization of the launcher volume, of the launcher payload, no prolonged stay of nuclear reactor in the near Earth environment, small perturbation, both from the point of view of altitude maintenance and also station keeping, so it's an easy place to assemble our huge structures, a higher starting energy, possibility of recover some energy exploiting the Hobart effect, and the lower braking cost upon the return. Saying this, I'm ready to explain you our strategy. First, a robotic core will be launched in Earth-Moon-Lagrangian point 1. Second, some support structure will be also launched to Earth-Moon-Lagrangian point 1 and assembled Once the structure were assembled, propulsive module of the Mars depot will be also launched in Lagrangian point 1, and the Mars depot will be refueled. So, once the Mars depot is refueled, can start his cruise from Lagrangian point 1 to Mars. In the meanwhile, we'll start assembly the manned spacecraft. So Columbus module is launched in Lagrangian point 1. Also support structure will be launched in Lagrangian point 1. And the manned spacecraft will be refueled. Only when the propellant depot will be located at Mars, we will send the manned crew on the Lagrangian point 1. The crew will be transferred from the crew transfer vehicle to the Columbus module. During the cruise, the manned mission will burn all the propellant. And when the manned spacecraft will reach Mars, we will transfer the fuel from the Mars depot to the manned spacecraft. So the fuel is transferred, therefore the manned mission can start, can come back, the manned crew, again, burn all the propellant, will come back to Lagrangian point 1, the crew will be transferred from the Columbus module to the crew transfer vehicle, and the crew finally can come back to Earth. And slowly, the Mars depot will return Earth. We return in Lagrangian point 1, sorry. So this is aimed to be a steady state configuration. So as I said before, the servicing is going to be performed each 2 years. So this is going to be a steady state configuration. I want to stress the attention on this point. So let's take a fast look on the assumption we made on the launcher's availability. We have huge masses, and our mission is going to start in 2028. So we assume to have available 2 launchers for year, 2 space launch systems for year, 13 Falcon Heavy for year, and an indefinite number of smaller launchers. But in any case, even relaxing some hypotheses on near future launch capability, we see that the launch windows in 2041 and the launch windows in 2043 are not feasible in any case, even relaxing the previous vehicles. So let me give a preview about our vehicles. So we call Ares the Mars depot. We call the Omade the manned spacecraft assembled with the Columbus module. We call Tank the refueling component, and the structural component. Icarus is the module proposed to bring all these single components in Lagrangian point 1, and the core is the only permanent structure in Lagrangian point 1. Now I leave the word to Fabrizio Sassi, who will give some more detail about the Omade, which is the manned spacecraft.
Okay, I'm Fabrizio Sassi, and I will talk to you about the Diomede manned spacecraft. I remind you that this is the vehicle that will have to travel to Mars and back in a time window limited to 250 days. This is a hard requirement. Here we can see the vehicle's general configuration, and we see that it is mainly made up of a truss structure built with modular segments, the tank modules, which again are modular and divided in 3 standardized sizes. Then at the front end, we can see the Columbus-like payload module, the thrust propulsion module, which stores some storeable propellants for attitude control. And finally, at the aft end, we see the heat shield, which protects the tank modules from sun radiation, and finally, the ANERVA nuclear propulsion system. Here we see an example of a mission profile that Diomede will have to perform. And the most important fact is that the interplanetary transfers are made of short Lambert transfers, which, while obviously much faster than a standard Hohmann transfer, are also much more energy intensive. In order to try to reduce this very high cost, we elected not to perform the escape burn directly from low Earth orbit or low Martian orbit, but instead start with our vehicles respectively at Earth Moon Lagrange point 1 and higher areosynchronous orbit, then to lower our percenter and perform the escape burn there. This gives us a net saving of about 2.4 kilometers per second when escaping from Earth, and about 400 meters per second when escaping from Mars. In order to be able to perform this very peculiar mission profile, we elected to use a nuclear propulsion system. This is due to a number of advantages that such a system has. First, it has already been tested, albeit only on the ground. and offers a very high specific impulse, approximately double that of that obtainable today from chemical systems, while still maintaining a good thrust-to-weight ratio. This is very important since our trajectory is a very fast trajectory. This system also has a number of disadvantages. Most important the fact that this technology has never been flight tested. Some smaller reactors have been flown, but never in such a configuration. And that, of course, a very high power nuclear reactor is needed. We performed our sizing taking into account some of the improvements that we expect to be available by the year 2028. Most importantly relating to the obtainable chamber temperature and obtaining the following results. So while the engine is quite heavy at about 7 tons, it is important to note that the shield, the radiation shield, takes up a significant portion of this mass, but it is obviously a necessary expense that we need to make in order to protect the crew and the other spacecraft components. Regarding the feeding system, it is important to note that our standardized tanks are to be used not only on the Diomede vehicle, but also on the Mars Depot, the RS vehicle, which has an electric engine, which has a much lower mass flow rate. In order to be able to accommodate both the high mass flow rate functioning of the nuclear thermal engine and the low mass flow rate functioning of the electric engine, we elected to use the self-pressurizing nature of the hydrogen, which will have reached a temperature of about 20 Kelvin, so a tank pressure of about 1 atmosphere once it is to be used, augmenting this pressurizing system with a pressure tap from the nozzle of the nuclear thermal engine when it is being used. Finally, a short talk about the attitude control system of Diomede. It has 2 main goals. First is to guarantee a sun pointing attitude during the interplanetary transfers in order to put the shield between the sun and the propellant tanks. Finally, it must also ensure fine attitude control in aerosynchronous orbit for proximity operations between Ares and Diomede, since these 2 vehicles will have to dock together. To accomplish this, we selected star tracker sensors and, for proximity operations, videometers and telegoniometers. The most important feature of our attitude control system is the fact that our control moment gyroscopes, namely our main mean of controlling attitude, are distributed along the standardized thrust segments. This has the important benefit of allowing the control authority to automatically scale up and down with the varying vehicle configuration, which has to change quite a bit between different windows. Finally, some results in this regard. We see that the control moment gyroscopes, which are positioned in a standard tetrahedron pattern, are quite heavy, but due to the very high length of the vehicle and thus the moment arm, the propellant needed to desaturate them is actually very low. Finally, a short look at the mass and power budget of the vehicle. This was taken using 20% margin and the worst case configuration that was encountered, namely the one that required the most amount of propellant. We see that in this case, and all the others, but in this case especially, a very high percentage of the mass is taken up essentially by the fuel modules and their fuel content. So I will now give the word to Marco Magnani, who will talk about the Ares Mars Depot vehicle.
Good afternoon, everybody. I'm Marco Magnani, and I'm in charge of the APS subsystem. Now I'm talking about the Ares, the tower refueling depot. Mainly is composed by the same thrust structure and tanks of the Diomede, but in this case, some of these tanks are used to driven the propulsive part that is composed by a nuclear reactor and an NPD thruster. Since we have extremely large payload to move, we need a very high thrust for a long period of time. So the only possibility is to use a magnetoplasmodynamic thruster that has an extremely high specific impulse and can be used for our special requirements. Then since the lifetime is not enough long, we think to assemble them in a cluster that is changed at each mission of the RS. And also it contains the propellant for the DCS. So the pros of the migrator plasmodynamic thruster is that has a better thrust weight ratio of the thruster we use nowadays for electric thruster, and use the same propellant of the manned mission, so we can use the same tanks. So with a cluster of 12 thruster, we can achieve our goals, but the power consumed is extremely high, more or less 10 megawatts. To achieve this, we must use a nuclear reactor system, and mainly is composed by a nuclear core and a Brayton cycle for the power conversion. The main issue here is to size the nuclear reactor system and the radiator size. That must be extremely large. To size the nuclear reactor system, we use a regression law between the thermal power produced by the nuclear reactor and the mass of the entire system, using existing nuclear reactors tested for space. Then, in order to subdivide this mass in the main components, we use these two systems that are already tested on ground, so we can see the subdivision of the total mass in the main components. Then the other main issue is to size the Brayton cycle, so we use, in order to size the power needed from the reactor and the power that has to irradiate from the radiator, and so the radiator area. So with the requirements we have, with the total mass of 14 tons, that is the largest mass launchable in the Earth-Moon Lagrangian point, and with this power needed, we have a system of 39.3 tons and a radiator area extremely high, but we can still consider it as a part of our regression law. Then, since the radiator has to irradiate a lot of power, we think to shield it completely from the spacecraft to avoid heat conduction and radiation to the liquid hydrogen, with MLI and also low conductivity connection with titanium and aerogel. Then for the radiator deployment, since it was quite large, as you can see, we to make a foldable configuration that is opened after the launch when the nuclear reactor is started, and is made by rigid petals to allow the internal piping. Finally, for the DCS, we use the same system for the Omega, since we have the same truss elements. And here is the mass and power budget. As you can see, since the payload mass is quite a large part, because we have used an extremely efficient thruster method. And now I leave the word to Matteo.
Good morning, everybody. I'm Matteo Romano. I'm in charge of the mission analysis part of the project Ardent, together with Simone. And I'm going to show you now how the RS relocation works. You can see here a brief overview of the main phases of the transfer, which exploits both the natural motion between the Lagrangian points of the Earth-Moon, Earth-Sun, and Mars-Sun systems, and a continuous thrust arc. This kind of slow transfer was chosen because of the high payload mass the RS has to relocate on Mars in order to service the human vehicle, and which make the use of low-cost transfers and of electric propulsion very appealing in terms of propellant consumption for the trip itself, while a chemical or a nuclear approach would require much higher masses. So the RS relocation starts on the Halo orbit, where it is assembled around the Earth-Moon Lagrangian 1 point, where a maneuver puts it on an unstable manifold, and then on a stable manifold, going to another halo orbit, a waiting halo orbit around the Lagrangian point 2 of the Moon system. Here you can see in this table and in the following, you can see indicative values of cost and times. Yes. And the second phase, after the waiting on the halo orbit, is composed of a transfer along an unstable manifold going out of the Earth-Moon system, and then on a stable manifold of the Earth-Sun system going to a halo orbit around the L2 point, where a new maneuver brings it on an unstable orbit, unstable manifold going toward deep space. After this, after enough distance from the Earth to consider its attraction negligible with respect to the Sun, the MPD engine is switched on, and a continuous thrust maneuver transfer is performed in order to reach a final point with a precise position and velocity in order to insert on a last manifold a stable manifold of the Mars-Sun system going to an halo orbit around the L1 point, where a new maneuver, a last maneuver, brings Ares on an unstable manifold going closer to Mars. And at this point, a series of maneuvers begins in order to lower the orbit and insert on the aerosynchronous orbit around Mars. First, a braking maneuver in order to obtain high eccentric orbit, and then a series of distributed burns near the pericenter in order to reduce the eccentricity, and then near the nodal axis in order to reduce the inclination of the orbit. And after the last maneuvers, and a series of last maneuvers in order to insert on the operational orbit. And you can see here the complete transfer going from the L1 orbit around the Moon and around to Mars for the Earth-Mars transfer and for the back trip. In the example of the 8 window, which was chosen in order to size this kind of transfer, because it is the case with the it is a worst case with the highest payload mass of the Ares. Now, after the two vehicles, Diomede and Ares, are on the same orbit, Diomede, in this case, becomes a chaser and performs a series of maneuvers in order to approach and dock with Ares. In this case, the chaser is Diomede and not Ares, because of its lower mass with respect to Diomede, Ares, sorry, because it's almost all the propellant has been used up, and the possibility to perform impulsive maneuvers, so fast maneuvers. And after the two vehicles are safely docked, the Icarus modules transfer the propellant tanks from one vehicle to the other with an autonomous action, which can be, however, the humans can take the control manually in case something happens. Here you can see the profile this distance was considered in order to increase the safety of this kind of operation. And now I leave the word to my colleague Simone, which will speak about the
Hello everyone, my name is Simone Rafano Carnai, I'm in charge of the mission analysis section together with Matteo, and today I will talk about the tanks and the Icarus service module that are very important in our mission. First of all, the tanks, so you can see that we decided to use 3 different sizes of tanks in order to optimize the launcher capabilities and the on-orbit staging. But you can, the most important things are the dimension of these tanks. You can, for example, compare this with our colleague Riccardo. that the three tanks are very, very big, and of course the thickness is quite small in order to decrease the structural ratio, and this gives up to two problems, two main criticalities. The first one is the fact that we have to launch these structures, and the second one is that inside we have a liquid hydrogen, and so we have a very huge critical in terms of cryogenic propellant. So first of all, the tanks boiling off problem. We selected the RS strip, which is the worst case solution. So the smallest tank, which has the lowest mass over surface ratio, is the most, let's say, the worst condition, because it can be heated up very fast. And the worst case condition is the RS strip. So there are a lot of phases with different distances from the sun, which means different solar fluxes that reach the tanks, and different conditions in terms of shield, that I will show you why we have these conditions. But the important thing is that we are able to satisfy the worst condition with two solutions. So the first one is an active solution but on ground. The second one is a passive solution on space. At the end, I will show you also a backup solution in order to increase much more the time that the tanks are able to permanence in space. So first of all, an active solution, I will go very fast because it is not our work, is a NASA study which practically spill up some hydrogen from the tank and cool it down up a very lower temperature with respect to the boiling off temperature, and this allows to stay in space for a long time, because we can just wait that the temperature grows up to the boiling temperature. Since the heat coefficient of the hydrogen is very high, we can wait a lot of time before the temperature can grow up again to the boiling temperature. So this is the most important part of our subcooling technique. Then we can use a passive strategy. We cover the tank with an MLI insulator. In this way, we can reduce much the flux that reaches and enters the tank. And this allows us to increase a lot and much more the time that the tanks can stay in space. And in addition, we introduce also the solar shield, which allow us to reduce much more the heat that pass through and reach the tank. With this, with all these strategy, we can simply reach at the end of the worst condition practically the temperature of the boiling off. So we are fulfilling the final requirement in terms of temperature. Of course, here we talk very conservative assumptions. So this is a very good results. And in addition, we can also use another approach if, for example, there are some problems of some issues in terms of temperature, because as Matteo shown, during the travel, Ares has to perform continuous thrust maneuvers, so it is not possible to orient the spacecraft with respect to the sun to protect the tanks with the shield. And so what we can do is just to spin the spacecraft in order to distribute the heat on the different tanks. Okay, this is of course additional complexity, because we have to spin, of course, a very large structure, but it can reduce strongly the heat that reaches the single tank. Then this is our most conventional spacecraft, so I will go very fast with Icarus. This is like a third stage of launcher. It is actually very useful because it allows us to bring all the different components on the ML1, and in addition to transfer the tanks from Diomedes to Ares. So it has all the different tanks for the fuel, for the oxidizer, the low gain and medium gain antenna, and solar arrays. This is the mass power breakdown for Icarus, and we can see that the most important part for the mass budget is the propulsion system. Then the other, as I told you, the other problem was, the other criticality was to launch these structures. So we we did a FEM analysis inside the launcher in order to compute the natural frequencies of the system. So we created an assembly which is composed by a service module, an adapter skirt, which is very, very important. This is quite innovative because it allows us to distribute the loads on the tank and so increase the natural frequency of the system. And then we have, of course, inside the tank and the liquid hydrogen. The tank, as I told you, is very big, and the thickness is quite small. So we achieved the result in terms of natural frequency introducing the component materials. This is done by an external layer, NOMEX intermediate layer, and an internal layer. Again, with carbon epoxy, which allow us to optimize the strategy between bending stiffness and pressure inside the tank. These are the results, and we can see that we satisfied both the static and natural frequency load with a margin of safety of 2.2. Now I show you very quickly the trajectory that allows us to bring the single components with the Icarus module up to the halo orbit. So we just follow two paths. The first one is an eccentric orbit, and then we jump on a stable manifold to reach the facing halo orbit. I said facing because actually when we arrive on the Earth-Moon Lagrangian point 1, we have to face the two vehicles in order to perform then the rendezvous. This is done, so first of all we have to compute the phasing point. This is done using the LVLH reference frame, which is quite different because it is centered with respect to the Lagrangian point. We computed the long track and cross track, the LVLH coordinate frame and transform this in terms of a long track angle, and we can compute quite easily the phasing point. The phasing point means that we are on the vertical, we have the two vehicles aligned on the vertical axis. And then when we are at that configuration, we can perform the rendezvous. So we do it with a series of 7 maneuvers, 5 for the initial approach and last 2 for the final approach. These plots are, the 7 maneuvers are plotted in terms of LVLH reference frame. And here there are all the different values, also in terms of time of flight, which is 15 days. When we end up with the final approach, we have to perform the final translation, which means the last 500 meters, which is done with a continuous thrust trajectory using a linear model, which is the Farcar model and L-Quare controller. Finally, it's very important also during the rendezvous and the docking, the OBDH and the GNC problem, because we are very far from Earth. We cannot transmit whatever we want because we are quite far. So we decided to use different sensors, visual sensor, optical sensor, and also radar sensor to obtain a robust system. Now I leave the word to my colleague Alessandro, who will talk about the final vehicles.
Thank you. Good afternoon, everybody. I'm Alessandro Serboli. I'm the responsible for the structural subsystem. I want to present the main structure, the permanent structure we have in Earth-Moon Lagrangian point, which is the core, and the trusses, which are the main structure of Ares and Diomede spacecraft. Let's start with the trusses. We have two different sizes. This because we have different sizes for the tanks. For example, the truss of 12 meters can host also the big tanks, the tank of 40 tons, whereas the truss of 9 meters can host also only the medium and small tank. As you can see in the figure, each truss is provided by 6 docking parts. 4 of them are available for the tanks, whereas the other 2 are needed for the assembly of the beam. You can look at the control moment gyros inside the beam in order to keep the attitude. But let's give a look to the structure more in depth. We have performed a finite element analysis. You can see in the table the main components we have modeled. The truss member is tubular, and we have selected carbon epoxy material because it provides the highest stiffness to density ratio. And this you may understand if you look at the right side, where you can see the launch configuration. And we have chosen to launch the two beams attached one to the other in order to decrease by half the number of launches, since even in this case we are obliged to use the SLS launchers. You can see also the Icarus service module that has the task to bring the structure till Earth-Moon Lagrangian point. If you look at the results, we have taken the delta for EV requirements because we do not have any information about future launcher. You can see the result. We can provide a safety factor of 2 for the bending frequency and no problem on the static loads. But let's look now to the core system. In the figure, you can see the main components, the robotic arm with the end effector compatible with the docking port. But first of all, let's try to understand why we have selected the core. We have, as already explained by my colleague, the human transfer might differ a lot in terms of delta V. And if we add size the beam, fixing the length, of course, we have to size the beam according to the worst configuration. And this means to bring with us the dry mass we are not going to exploit. Instead, with this modular approach, we are able to assemble the right dimension, the right number of beams in order to perform that precise round trip. And you can see the difference in terms of Diomede and Ares for the configuration of the spacecraft. If you look at some results in terms of mass, the mass might differ a lot, more than 20 tons. And if we consider all the mission, the whole mission during 50 years of mission, we can save 40% of mass using the core system and assemble the beam. So just a quick look to the structure. I want to point out that we are obliged to fold the robotic arm in order to avoid coupling with the frequencies of the launcher. And in this case, we are obliged to use 4 cables, carbon fiber cables. And if you can see that the result is satisfied with a safety margin of 2 at least. A few words about the telecommunication system. The core is provided by 2 different antennas, one low gain antenna for the near Earth operation and the high gain antenna for all the rest operation, and in particular for the docking operation. You can see on the table that the highest data rate occurs during the docking phase. And you can look at also at the link budget. Just to conclude, a mass and power budget, just look at the fact that the largest amount of electric power is needed by the robotic arm. This is the robotic arm. I give you a comparison parameter with that of the International Space Station. You can look that the ardent arm is very long, 30 meters. This because we have to reach the second beam in order to correct assemble the beam. You will see in the video next. 5 degrees of freedom are enough for our case. We are performing standardized equation, and the mass handling capacity is fixed by the nuclear reactor. So you can see the video. This is a simulation performed in Adams. On the left side, there are 2 beams with the nuclear reactor attached. The core, you can see, we avoid to control it. We avoid to keep fix it because it's a too demanding maneuver. But there is no problem if the core rotates, because if the axis of rotation is perpendicular to the plane containing the sun and the Earth, we can easily reorient both the antenna and the solar arrays. I show you an example of a reconfiguration of the Diomede spacecraft. You can see on the top what is happening. We have a Diomede spacecraft on the left side, made of 2 beams. We want to enlarge it. We want to increase the length in order to serve the next time window. So the robotic arm moves the beam in order to correctly assemble. In this way, it takes the Diomede spacecraft and attached to the 3rd beam. At this point, there is no Columbus module attached, so the robotic arm moves the whole spacecraft and attach it to the Columbus module. When the radiator shield opens, the Diomede is ready to be detached from the core. Just the final slide, it's an interesting outcome of the use of composites. since we have modeled all the emissions also with metallic material, we can tell you that since the structural coefficient of the tanks is strongly involved in the Tsiolkovsky equation through an exponential law, and since we are making an intensive use of the staging approach, the mass saving is much high. You can see 200%, which means more than 7,000 tons. I can leave the word to my colleague Alberto now.
One moment. Okay. Hi, everybody. I'm Alberto Napoli, and I'm going to introduce you to our timeline. As you may understand, our timeline is really complex, and I don't want to go into too much detail. I just want to underline some basic concept. So first, again, the time span of our mission is 30 years, and we are going to perform 10 manned missions on Mars. As you can see, the first thing is that we need 4 Ares vehicles to perform our missions, because Ares takes a long travel to Mars, 3 years, due to the continuous thrust, while Diomede has an impulsive maneuvers and takes a rather shorter path, also because it is a requirement of the mission. Moreover, another thing I want to point out is that Diomede always starts the trip from Earth to Mars just when Ares depot is already on Mars. This is due to the fact that we don't want to leave human crew alone in the space, and we want to be sure that all the fuel is already located when we start. Last thing I want to show you is these black lines that are the period of inactivity. Due to the fact that we are cutting 2 of the most demanding launch windows, we have a long time of inactivity period for Diomede and 2 of the Ares. And of course, this period can be used to service other missions, since we already put into, let's say, into our design a lot of structures and a lot of things going on. So we can maybe think to use in those periods our structure to help to create a Martian base or lunar base by servicing it or bringing there the modulus. Or we can even think to create an LM1 space station using the core as the first step. Of course, if we manage to do so, we need to revise the design of the core and of the arm. Really fast now, since the time is running out. So the risk analysis, our mission is really, really complex. We have a lot of things going on. We just use the risk as a driver to select the mission architecture baseline and to think about our subsystem design in order to create some backups. And the main driver, again, is the crew safety and the human safety. One of the trade-offs we made, it was the Mars refueling selection. So as my colleague said, we are performing a tank switch. That means that we are switching all the tanks from Diomede to Ares. And with our computation, we saw that we can afford to lose some of the tanks and still be able to bring the crew back to home with an increased 30 days travel. And so this approach uses more operations and, of course, less criticalities. On the other hand, engine switch, of course, the idea is just basically changing the switch, the engines between the 2 spacecraft. But of course, on one hand, we have less operation. On the other hand, we have high criticalities. So we focusing again on the human safety. We did some trade-off based on risk and diagram. And we can, for example, see that the engine switch failure as an acceptable risk. So we actually perform a baseline change, and we went for a tank switch failure. That actually is a low acceptable risk. And through measures of prevention and mitigation, we can decrease it even more. For example, with docking system backup or manned guided docking. And the same for the sun shielding failure. We realized that our mechanism is not so strong, but still the risk is not so high, it's low. We need to improve it, of course. It's an open point. 1 minute on cost estimation. We have a lot of new technologies, so we basically did an analogy cost estimation with parametric cost estimation just for Icarus that is quite standard. And we use adjustment factors to take into account the TRL, the heritage design, and the learning curve models. So the final cost, of course, it's as expected, it's pretty big. It's more or less $380 billion. And this is, of course, I want to remind, to a 30 years mission with a lot of new technologies going on. As we can see, for the cost drivers, of course, the aim of this is not to give a detailed cost, but to give the weight of each part. The launchers and the developing of nuclear technologies and MPD technologies are the most demanding one. Finally, we made a strategy trade-off. So once we fixed our baseline, we started to discard one of the worst launch window out of the 5 we took at the beginning. And we discovered that we can have a 17% of mass reduction on the overall system. And by relaxing the requirements of the travel of Diomede, increasing it by 30 days, and of course, including the radiation shield mass to prevent human damage to the health, we have a global reduction of 30% of the mass. So of course, these are trade-offs that can be used in the next phases of the project to maybe understand the design of the system. Finally, I would like to close with a quote. It is of Marcus Aurelius, and a man's worth is no greater than his ambitions. It's kind of guided us through our design, since this was really a demanding project, but at the end we enjoyed it and we were able to do it. So thank you for your attention.
Yes, of course. I will start to answer you, starting from our last trade-off. I mean, our configuration messes during project development changes a lot of time depending on the margins we took and different margins on the shields, let's say, or on many things. So Columbus is like, for us, is like a mess, let's say, but during the phases of the project, we saw that our configuration with the core and the robotic arm and the possibility of customizing the length of the spacecraft and the refueling operations, we see that our configuration is robust on the payload of the mission, and also, of course, on the Columbus payload. Let's say the trade-off is, let's say, if we want to use 30 days more of travel, which is not good also for a manned trip, because astronauts cannot. 250 days in deep space in a Columbus module is not the happy condition to travel, but increasing of 1 month the payload of the Columbus, we have enough shield to support a longer mission and a low-cost mission, re-entering in an acceptable number of sievert from literature. Obviously, is not a univoc in this sense, but re-entering in an acceptable number of radiation. Thanks a lot. Yes, other questions? No? Okay. Sure. Yes.
Because I think in the investigation you mentioned the story of radiation. The two big problems that you have in, let's say, long duration mission, radiation and absence of gravity. So those are two things that you have to travel with people for this duration.
That this is 250 days. Let's say the assignment of the mission was to create an infrastructure capable of supporting this payload and this travel. We also made some studies making longer travel.
I think I saw the sizing of the radiator for nuclear reactor. So I agree on all the points, not on that one, because they presented it.
Which one, sorry?
The radiator for the nuclear reactor. But they can answer.
Okay, very good. But then, let's say, should be very good. It's not necessarily sure. But then, the thermal design provision should take care also of all the heat also coming from Columbus, from all let's say, the provisions that we have accommodated in the, let's say, habitation module in that case. It will be more than a space laboratory.
No, just we can give an answer.
Okay, for the what concern the thermal part, our focus main problem was to keep hydrogen cryogenic. So we didn't exploit the problem of the thermal part of the Columbus, like you evidenced. But all connection with from the nuclear reactor and the tank and the Columbus are just a small beam, and all connection is have a thermal washer based on the use of the titanium and the aerogel that reduce conductive heat coming to the tank. So our worst problem was the thermal heat coming from the sun, and we neglecting the radiator because of this stuff. And of course, we exasperate our analysis because we hypothesize always the half surface of each tank is always in front of the sun. That is statistically is not so probable. So we take the margin in that sense, but we know that all thermal part is work in progress and could be improved.
Yes, regarding the issue of the radiator of the nuclear reactor. What you've seen was the radiator of the nuclear reactor of the RS vehicle, of the depot. This is a smaller reactor which has as its scope the production of electric energy, essentially. For the diameter vehicle, you are correct in that we didn't include a radiator yet. Mostly because it was very difficult to find hard data on the thermal output of an idling nuclear reactor. However, it is important to note that during the cruise flight, the nuclear reactor of the diameter vehicle is idled or shut off, and during its firings, it is cooled by the hydrogen flowing through. So yes, that is an aspect that needs to be studied a bit further, but just to clarify a bit.
Only to choose the location, it takes ages. So.
Vai.
Ah, di qua non conviene.
Questo lo vedi leggermente ritardato.
Ah, ok.
Questa funziona tranquillamente per la spostazione.
Aspetta. Ah, di qua non conviene.
Questo lo vedi leggermente ritardato.
Ah, ok.
Questa funziona tranquillamente per la
Posso andare, prof?
Okay. Good afternoon, everyone. My name is Andrea Filosa. I'm the actual team leader for this Tetris team. As you can see here, Tetris stands for Tether Debris, and our mission... Wait. Okay. Our mission is... our primary objective is to perform an in-orbit demonstration for anti-debris, everyone. My name is Andrea Filosa. We had to deal with some mission requirements, including one of the most important, as you can see here, Tetris stands for deal with a chaser mass less than 10 kilograms, to deal with an operative lifetime less than 1 year. The launch date shall be before 2017. Our primary objective is to perform we need to assess the demonstration feasibility control. We had to deal with some mission requirements. For this, one of the IOD mission here, this is what we are going to perform. So the chaser target relative state reconstruction, operative lifetime, target at here, reconstruction, the validation of the new software by PoliMi, which implies the capture phase and the tether system. And we had to deal with. We also want to increase for this one of the efficiency here. This is probably designed. We are going to analyze this. So we want to analyze the reconstruction, the object target at here, reconstruction, the performance analysis of the object which are coefficient tether system. This is we also want to increase but specifically we are going to analyze this. We want to must analyze the typical grounding of object target at here, reconstruction, the performance analysis of the object which are variation and tether system. This is we also want to increase this is our specifically we are going to let's speak about time. As you can see here, our ground line of object the commission phase up to the performance analysis of the operative lifetime which are variation not recovery. This is we also want to increase this is our specifically we are going to let's speak about time. As you can see here, our ground line of object the commission phase up to the performance analysis of the operative lifetime which are variation not recovery. This is we also want to increase this is our specifically we are going to let's speak about time. As you can see here, our ground line of object the commission phase up to the performance analysis of the operative lifetime which are variation not recovery. This is we also want to increase this is our specifically we are going to let's speak about time. As I was saying here, for the operation the commission phase up to the get performance analysis of the operative lifetime we are so in fact there are as I was saying here for the commission phase up to the get so and destroy I know that this is so in fact there are as I was saying Speaking about drivers, this configuration for this gas source. So, all the different conditions have a choice. Speaking about drivers, that's the conversion to our gas source. So,
Thank you, Luca. Good afternoon. I am Leonardo Marigliani and I am in charge of the propulsion system and of the risk and cost analysis. I will give you a quick overview on the risk and cost analysis we have performed. First of all, for what regards to risk analysis, we have based a method on a three states both for the probability and the impact of each risk.
Thank you, Luca.
Good afternoon. I am Leonardo Marigliani and I am in charge of the functional risks when managing each subsystem. I will give you, we found out that there were critical risks. We have mission risks, first of all, where what regards to risk analysis, to the based since the payload method on three critical states and one both for the first time explaining the impact of each risk. For all of them, we have the original one risk situation, which is very bad since each subsystem. Probability, we found out that there were regular risks. We cannot accept risk, first of all, where we have to mitigate risk analysis. Mitigation for all the three risk methods will ensure a critical state is aimed at reducing the probability. For all of them, we have the original one, but the risk higher, which is very bad, means that each subsystem probability. We found out that there were regular risks. We cannot accept risk, first of all, where we have to mitigate risk analysis. Mitigation for all the three risk methods will ensure a critical state is aimed at reducing the probability. I will also look at the original one, but the risk higher, which is very bad, means that each what regards probability. We found out that there were regular risks. We cannot accept risk, first of all, where we have a standing, which is mitigation. First, for all the three risk methods will ensure a critical state is aimed at reducing the probability. I will also look at what can be the original one, but the risk higher, which is very bad, means that each what regards probability. We found out that there were regular risks. We cannot accept risk, first of all, where more or less a standing, which is mitigation. First, for all the three risk methods will ensure a critical state is aimed at reducing the I will also look at what can be the original one, but the risk is very bad, means that each what regards probability. We found out that there were regular risks. We cannot accept risk, first of all, where more or less a standing, which is mitigation. First, for all the three risk methods will ensure a failure is aimed at reducing I will also look at what can be the original one, but the risk is very bad case, each what regards probability. Try to find out there were regular risks. We cannot accept risk, first of all, where more or less a standing, which is mitigation. First, for all the three risk methods can be mitigated with our failure is aimed at reducing I will also look at what can be the original one, but the risk is very bad case, each what regards probability. Try to find out there were regular risks. We cannot accept risk, first of all, where more or less a standing, which is mitigation. First, for all the three risk methods can be mitigated with our failure is aimed at reducing I will also look at what can be the original one, but the risk is all the work what regards probability. Try to find out there were regular risks. We cannot accept risk, first of all, where more or less a standing, which is mitigation. First, for all the three risk methods can be mitigated with sources which we have lost trading on that, but it is all the work what regards probability. Try to find out there were
Will be
Our
Yes.
This Again?
And we have
water car, maybe something like a small error chipper can be track the surface because we expect the sample mass regularly. So we need to create the flow of gas, the chipper gas, the lateral plane. Okay, the rock chipper gas in lifting sample projectile at the same time something like a definition of a chipper that can track the surface we expect the gas regularly. So we create the flow of gas, the chipper gas enters the chamber. Here the rock chipper gas in lifting sample projectile at the same time with the rest of the gas like a slow definition of a chipper that tracks the surface we expect the gas regularly. So camera creates the flow of gas really small and enters the chamber. Here the rock chipper gas in lifting sample projectile at the same time with the rest of the gas like a slow definition of a chipper. Yes, the robotic the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample projectile at the same time with the rest of the gas like a slow definition of a chipper. Yes, the robotic the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample projectile at the same time with the rest of the gas like a slow definition of a chipper. Yes, the robotic the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample projectile at the same time with the rest of the gas like a slow definition of a chipper. Yes, the robotic the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample projectile at the same time with the rest of the gas like a slow definition of a chipper. Yes, the robotic the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample projectile at the same time with the rest of the gas like a slow definition of a chipper. Yes, the robotic the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample the camera creates the gas really small and enters the chamber. Here the rock chipper gas in lifting sample the camera creates the gas
Mannaggia.